You guys can hear me at the back? Yeah. Okay, so thank you, Barbara, for the introduction, and I apologize for the fact that your slideshow did not like my computer. So hopefully it likes my own slideshow. Okay, so I'm really glad to be here, and thank you all for being here. And as Barbara said, I'm going to talk today about time, but we are going down to very short times, microcosms of time, and I'm going to explain what that means in a bit. So, I'm the sixth person in this series. So if you have been attending it regularly, my colleagues have been giving beautiful talks on various aspects of time here, and Pierre Maestre kicked off this series with the talk titled "It's About Time," and in this talk he covered various topics, and he explained the human interest in time. It's a strange thing. So he explained how have humans come about to measure time, right from years, months, days, hours, seconds, milliseconds, or even faster, and how atomic clocks are playing a role in this now by helping your phone catch the GPS signal from satellites which have atomic clocks on them, and the timing from those clocks helps you navigate and find the directions. So it was an amazing talk. I had a chance to discuss that with him, and he also told you that time is not an absolute concept. Time is relative. Okay. And he discussed the fact that Einstein has told us that space-time is a kind of a fabric. So for example, if you had an event happening here, the information about that event will be carried fastest by the light. That's the fastest possible way. And as the time goes on, the information can go to larger and larger distances. So this is time in this axis and space along this axis. So information can propagate further and further. But the speed of limit decides how far the signal can go, how far the information can go. Okay. So this is called light cone. So he explained all that in his talk. And then Thomas Fleming picked this up on this end, very large times and very large sizes. So he discussed what's happening on cosmological timescales, formation of galaxies, evolution of the universe. Okay, so he discussed all that, and then Jessica Kopp brought us down to Earth with what's happening on Earth. Okay, what's the life of, what's the history of Earth, and how do we date things that happened on Earth? How do we measure? How do we do carbon dating? How do we measure how old is a layer on Earth? And then Brian Enquist took us to biological systems. He explained us how long things live and how is their lifetime related to their size. So he discussed things from years to hundreds of years. So we have come down from billions of years to hundreds of millions of years to hundreds of years. And then Fabian gave this talk on a very interesting topic of psychological aspect of time. How do we perceive time? Okay, so everyone may have a different perception. In different situations, you may have a different perception. So it's amazing. And now what I'm going to do is to take you beyond what we can perceive. Okay, so something that you cannot really fathom. It's so fast. And you notice that faster, the shorter the durations, shorter the sizes. Remember, this side is size, this side is time. So shorter I go in time, it becomes microscopic objects, right? And it's related to that. So the question is, what happens faster than blink of an eye? Faster than what you can perceive? Any ideas? Anyone has suggestions? A gunshot. Very good. So, exactly my thought. Okay. So it happens faster than a blink of an eye. You will never see this picture with your eye, right? So, but I'm going to actually move even shorter in time, even shorter in distances, and even faster in time. Okay, and we have to enter this microcosm now, and it's not difficult at all. It's actually all around you, and I'll just say that molecules are in the air. Okay, they're constantly bombarding you right now. They're hitting you from all sides. Trillions and trillions of them are hitting you. Okay. And and they don't obey any speed limits. Okay, they do, but not so much. So if you were to look at in a dark room, you see this dust floating around, getting kicked around. It's those molecules that are kicking it around, and they're moving very fast. For example, this is dust particles. Let's say the molecules that are hitting them, they're not visible here, but they're moving at speed which is billions of times faster than this motion. Okay, so it can reach from a molecule in the air around you, a nitrogen in the air around you, or oxygen that you're breathing. It can reach from here to LA in 1 second. Okay, it's just that it just keeps hitting other stuff on the way. so, so it's amazing how fast things go. Now you might say, well, this is tricky. I can't see these things. So what are we talking about? So let's overcome that issue. Let's say I build a microscope which can actually see these molecules. Okay, see means at least visually perceive them, if not see their motion. So what you will see is that these molecules are actually rotating. Okay, they are not just translating, they are not just moving forward, they are rotating. And all of them do that. And their rotational time scale is pretty fast. This slide has been slowed down by a factor of, trillion. So the actual motion is trillion times faster than this. Okay, so I slowed it down tremendously to show it to you. And where does it happen? Where does it come into play? In your microwave oven. The moment you press the start button, these molecules start tumbling, and they tumble and hit other stuff, and they heat up your food. Okay, but they're doing it very, very fast. And then if you go further faster in time, these molecules are actually vibrating. Okay, not just rotating, they're vibrating. And this is happening now quadrillions of time faster, so 1,000 times more than trillion. Okay, really fast. And this is what's responsible for greenhouse effect. The light, the radiation, heat radiation that's reflected from Earth gets trapped in the atmosphere because it starts these molecules vibrating. Okay, now you want to see something more faster? You look at one of the atoms. Okay, in that atom there are electrons which are buzzing around. Okay, and they are really fast. They are pentillions of time faster than this movie. Okay, now pentillion is, of course, I'm going up in thousands, so it's million times faster than a trillion. Okay, so really fast. But it's what's responsible for everything that you actually see. It's the electrons jumping around that help you perceive things. The color of sky is due to this. The color of wine, the candlelight, it's electrons jumping around. Okay, so it's all around us. So the question is, how do I capture these motions? All right. So before we go there, let's do some basic math here. Okay. So I forgot to mention this. So I am going to ignore what's happening even faster inside the nucleus. Okay, that's high energy particle physics. So we're going to stop here. But in principle, you can keep on going. So and this stuff was known in theory by 1930s. It's just that we did not know how to visualize it, how to stop it, how to take a picture of it, like that bullet going through an apple. Okay, we did not know how to do that. So I'm going to show you how we can do that today. But before we do that, let's do some math. And the example that I want to give you is that, let's say you get your hand on a pile of dollar bills. Okay, huge pile. Are you sure you're going to wish that it was in $100 bills, not $1 bills, right? Easy for you to carry. So we do the same thing. We like to compactify our notation. So we, instead of writing thousands, we write 10 to the 3. Instead of writing million, we write 10 to the 6. Instead of writing 1,000th, we write 10 to the power minus 3. So we use this scientific notation. Okay. If I use this notation, I can put these numbers on my axis by the thousands. So this is 1 second, 1,000th of a second, 1 millionth of a second, 1 billionth, trillionth, quadrillionth, pentillionth. Okay, so it's incredibly short duration over here. Okay, but again, this sounds like a little abstract. So we come up with the names for these fractions. So we call them milli, micro, nano, pico, femto, atto. Atto means 10 to the power minus 18 seconds, attoseconds. Okay, so these are pretty cute names, the type of names you'd, for example, give to your cat, you know, pico or nano. So okay, so now we want to, we have this sense of numbers, at least how to write them. And let me give you the enormity. You know, it's okay to say this, it's 10 to the power minus 18, but what does it really mean? So our eye can see 1 second or a fraction of a second, 1/10 of a second. Electron is moving on 10 to the power minus 18 seconds. Okay, it's a huge number. Now, if I were to use the same factor that's between 1 and 10 to the power minus 18 and go the other way up to 10 to the power plus 18, we would end up longer than the age of the entire universe. Okay, so it's wide, enormous number here we are talking about. Okay, so we are going to that microscopic size of atoms and in looking at incredibly fast motions of electrons. Okay, now we didn't just wake up one day and said, hey, let's look at these fast electronic motions. People have been interested in it, you know, from ages, and people were interested. Can I see something faster than what's happening around me? What's happening on milliseconds, microseconds? So there was a progression, right? So first thing in this progression was, as often things are, was a bet. I don't know if you're familiar with it. It was a bet between Leland Stanford, who founded Stanford University, and a photographer, Edward Muybridge. And the bet was that when the horse is galloping, is there an instant when all its four hoofs are off the ground? Okay, or is one leg touching at all times? Okay, and the horse is galloping, so you can't see. Okay, so in 1872 in Palo Alto, they came up with a clever series of setup of cameras which would trigger when the horse was passing, and they could make this frames which I have put together in a movie. Well, I didn't, someone else did, but we put together a movie of those frames. So you can see that horses jumping around, and there is an instant where all its four hoofs are off the ground. So they settled the bet, and the time resolution was milliseconds in this case. Okay. So then people went further. You know, there was this guy, electrical engineer at MIT, Harold Edgerton, and he said, well, why not use strobe lights and sync them with the camera? You use it like a flash and capture very fast moving things. Okay. So so he did a lot of research in this field, high-speed photography and strobe lights and syncing them with different things, and he came up with a very clever set of pictures. He was actually hired by Atomic Energy Commission to image nuclear explosions because they were so fast. They wanted to know what's happening. So he developed this fast camera, and this is an image of a nuclear fireball. So at the bottom you see these trees here. So it's a huge fireball. So he captured what happens within a microsecond of the explosion. Okay. So pretty interesting stuff. And his lab took these kind of pictures that I showed you earlier. And the time resolution now is microseconds. So we are really going shorter in time. Okay. All right. So now the idea seems clear. So this sets the tone that if I had a fast flash, I could capture a fast motion. So if I just keep on flashing something, I can then capture a series of those frozen frames. Okay. So this picture shows you a baseball with great detail, all its seams and everything as this baseball is bouncing around. Right. It's fast flash of light. I just need a fast flash of light to go below a microsecond, to go to a nanosecond, picosecond. Okay. And sure, so that's what we have in the lab. Ultra fast flashes of light, which lasers help us produce. Okay? And they help us image fast motions like these, which are actually happening trillions of times faster. Right? So, of course, you'll say, well, okay, so what all goes in here? You know, how does laser magically make this happen? So to understand that, we have to understand something that Pierre told in the first talk a little bit. He said time and energy are related. Okay, so there is a relationship in quantum physics, which is Heisenberg's uncertainty principle. It says that spread in energy, or uncertainty in energy, and its product with uncertainty in time is a constant. So if one is larger, other one has to be smaller. Okay. So, and these, ignore these triangular symbols, they're just spreads, how wide energy spread is. Okay. So it tells us, this relationship tells us that if you want very small delta t, or very short duration time, you need to go to lots of energies. You need to have a lot of energy in your system, lots of colors, because energy is frequency and frequency is color. So energy is effectively is color. Okay. So that's what this picture shows us, that if you want a short pulse in time, very tiny burst of pulse, you need lots of colors in energy or frequency. You need all these colors here. All right. But it's not enough, actually. You need to do more in a laser. And what you need to do is, I mean, for example, if you're someone could have asked this, a kid could ask this, hey, but rainbow has so many colors. Does it mean that I can make a nanosecond pulse out of it? The answer is no, not really. And these lamps are emitting lots of colors. If I put a prism here, I'll see a lot of colors. But I can't make a short flash of light up from it. The reason is that these sources are incoherent. What that means is that the light coming from these sources is like waves. So all these colors here, one wave, second wave, third wave, fourth wave, they have waves which are out of phase. When you add them together, let's say at this time, at this time, at this time, the peak is on the trough. Over here, peak is on halfway here. So if you add all these values together, you get near zero values. Okay? Because there's no fixed phase relationship. The source is incoherent. The waves are all randomly going up and down for all the colors. The net result is flat line. So the lamp emits light, which is just flat with small fluctuations. Okay? However, if you go to lasers, photons have this property that it's coherent. Okay? When it's coherent, you can lock these phases. So you can sit at a time when all these waves have a peak. And then these peaks add up and you produce this burst of light. Okay? So the idea behind this is to lock the phases of all the colors. And that's why lasers are important, because lasers give us the ability to control this phase of the light. Okay? How light goes up and down. It gives us ability to control it. All right, so, okay, well, if you believe me, so we can make these very short pulses in the lab. And people have been doing it since 1960s, which is not too far back. And immediately they went from 10 to the minus 9 seconds, which is nanoseconds, and they went farther and faster and faster. They went to picoseconds, femtoseconds. In 1990s, they came down to femtosecond. Okay. Now this is much faster. This is optics, lasers. This is much faster than electronics can do. Okay. So no matter how fast your phone is, how fast you use your electronics, you cannot reach these timescales with electronics. Okay. You have to go to lasers and optics. Okay, so this is pretty common now. This line has flattened out, and you can, if you have interest and if you have some spare change, like $500,000, you can buy a femtosecond laser, no problems, just off the shelf. Okay? But what we are doing right now is we are going beyond this. We are trying to open a new frontier, which is going down to attoseconds. Remember, attosecond is a billionth of a second. So we are trying to go really short durations in time here. And it's been last 10, 15 years when this effort has been going on. Now let's summarize. Okay, so here is our arrow again. Second, millisecond, microsecond, nanosecond, picosecond, femtosecond, attosecond. On the top are the phenomena happening on these timescales. This is a picture of my daughter when she was 3 years old. And this is the horse I showed you, the bullet, the molecules rotating, vibrating, electrons jumping around. Okay. So at the bottom are the detectors we use. So you can see it with your eye here, okay? Or you can use fast cameras, but cameras and electronics don't work, so you use lasers, and lasers are commercially available to see this stuff. But now we have produced these new sources of attosecond light, which can study the electrons, okay? And it's not just we have a fast camera now, it's also a fast switch. We can use the same laser pulse to interrupt the process and control a very fast process, control a molecule. Okay. So it's both a camera and a switch. That's what laser pulse is for us. Okay, so we know how to see these fast phenomena. At least I can, in a few slides, I'll be able to convince you more. But now you might ask, well, before you go there, why do you bother about this? Why do we care, right? And as scientists, I could just say that, well, I just care because it's really interesting to me. I'm really curious about it, right? But we live in a society, and we have to make sure that that we are responsive to the society's needs. So we do things which actually benefit someone. So the fundamental science we are doing has applications, and I'll give you one example here. Let me go back here. Let me ask you this question. So you are looking at these slides right now, okay? What's happening is that the photons, the light particles, are bouncing off the slide. They're entering your eye and helping you see this, right? So one can actually ask a question now. How do you really see what's happening in your eye, okay? So femtosecond lasers have been used, people have used them to study this process of actually seeing. How do we really see something? What kind of reaction goes on in our eye? So we have found, and there's some detail here, that the photochemistry of vision is actually quite interesting. When the photon goes inside an eye, it excites an electron, and the electron finds its way through a conical intersection. And I'll explain later what a conical intersection is. And it passes through it in 50 femtoseconds, very fast, the electron, okay? And then what happens is that the molecule that we excited is called rhodopsin, and the rhodopsin experiences a structural change in about 200 femtoseconds. It starts to rotate and twist, and then within a picosecond, it finishes its twisting, it isomerizes, okay? And once it has isomerized, it has gone from this shape to this shape. That's when the next step can happen. That's when the chemistry leads to electrical signals later, and the electrical signals reach your brain, and then you see what you see, okay? So again, it's the femtosecond lasers that helped us see this fast motions that were responsible for actually seeing something, all right? So the femtosecond lasers, as I said, they're commercially available. They look like this. They are in our labs. So this is a picture from my lab. There's a lot of optics here, a lot of strong laser beams going through it, and behind it is a lot of technology, and the schematic is really complicated on how we control this light, okay? So there's no way I want to discuss this with you. So I'll just give you an idea of what's happening. So we plug something into the wall, which produces green light, and the green light excites a ruby crystal, okay? And the ruby crystal in a cavity produces this locked set of phases with all the colors in one time, and produces this tiny pulse of light, which is 15 femtosecond, but it only has very little energy, billionth of a calorie, okay? So if you're counting calories, it's very little energy that I'm using, okay? So, and now then we just do our stuff. We stretch this pulse, we amplify it 1,000,000 times, and then we compress it again, and we produce this light pulse now, which is 25 femtosecond, and it's a millicalorie, thousandth of a calorie, very tiny amount of energy, right? What can we do with this tiny little amount of energy in a pulse? Actually, a lot. Remember, the power of something is decided by this formula, energy divided by time, okay? Now I have very little energy, millicalorie, but the time is much, much shorter. Femtosecond, 10 to the power minus 15 seconds. If you divide these two numbers, you get very large number, 10 to the power 12 watts or terawatt, which is trillions of watts. And this power is more than the power of the entire electrical grid of the world, okay? So it's a huge amount of power, actually, because I could compress it all into such a short duration, the tiny energy produced a huge power at its peak here. Well, then you might say, well, whenever you plug it, do you just blow up the grids around you, or what happens? So, well, nothing. Actually, it's quite safe because I'm cheating here. I'm really not drawing too much power from the wall at all, because whatever I'm doing, it's only for a fleeting instant. Okay, it's for a very short duration. I cannot keep up with this power for a second. Then it will definitely burn everything if I do that. Okay, so it's only a femtosecond that I can do this. All right, so high power lasers are around. Everyone uses them now. Okay, people cut metals, they micro machine stuff with it, make micron size holes. You want to get a laser surgery, eye surgery, femtosecond lasers are used to produce precise incisions. And if you have so much power, you can focus it and create a plasma which is same as what's the plasma on the sun. So you can produce millions of degree temperature in the lab. So you can essentially bring the stars in the lab. Okay, so amazing amount of applications of femtosecond duration lasers. Just because you can produce a short pulse means you can do a lot more now. All right, so now there is another interesting question that pops up. You might ask, well, how do you know you have a femtosecond pulse? You might be just telling us you have a femtosecond pulse, you know. So how do we measure it? So to measure the bullet going through an apple, we use the flash. So the question is now, how do you measure a flash? Maybe with a faster flash. How do you measure a faster flash? With even faster flash. So this has no answer, right? So what you can do though is play a trick, and you can use the laser pulse to measure itself. Okay. So you basically, we developed this technique, which is very complicated. It's funny thing. It's called frog method. Okay, it's frequency resolved optical gating. So what you do is you take your light pulse, you produce two replicas of it. You send one straight away, one on the side, then you combine them back together in a crystal, and you produce new colors, and you detect these new colors as a function of time. You get a picture. And from this picture, you can figure out how wide your pulse was by reconstructing it. So it turns out it's 8 femtosecond in my lab in this picture. So you use the pulse to measure itself. It's an autocorrelation. Okay. All right. Okay. So now let's get back here. So I said we wanted to go to the attosecond regime. Okay. So how do we get faster than femtoseconds? Right. So femtosecond lasers are commercially available now. So now what we have to do is go back to this picture. This is a red light. Okay, so this pointer is red light. This is what this is. It's a wave of red light. Okay, it's a wave. Okay, and I know that simple calculations tell us that in this wave, the period is about 2 femtosecond from a trough here to a peak back to trough is about 2 femtosecond, and 1 femtosecond is about this much. Okay. It's about this much for this light wave, because this light wave is oscillating in time, right? So this window of 1 femtosecond is about this much. So now I want to produce a pulse which is less than a femtosecond, an attosecond pulse. Right? How do I do that? Well, I can't squeeze this red light in there, right? Clearly, its wavelength is much longer. You cannot do that. So the answer to this problem is to go to shorter wavelengths. Shorter wavelengths means X-rays. X-rays have short wavelengths. So instead of dealing with visible light now, you deal with extreme ultraviolet light or X-ray light, okay? The light that we cannot see. So this allows us, so this is what we do. So this is a spectrum which you might have seen that this side is visible light, infrared light, this side is ultraviolet light, X-ray light. Okay? So this is entire range of wavelengths or energies, whatever you want to call them. So now what we are doing is we are essentially going from here to X-rays, okay, to produce these attosecond pulses. Now, in my lab, this is how we actually produce these attosecond pulses. So the process is called high harmonic generation. It's an extremely nonlinear process. And the idea behind it is that you take this strong femtosecond laser pulse, which we already have in the lab, and shine it on an atom, which we can put somewhere in the lab, okay? And when it shines on it, it's so strong. I told you its power is terawatts. So it's so strong that it can create a spark, or it can rip an electron out from this atom and take it out. As it is going out, this wiggly laser pulse changes direction. It's going out, it comes back in. So it drags the electron back in. And it drags it back in so hard that when it hits the atom, it emits these X-rays. And that's the same process in the X-ray that you go and get taken from, medical office. It's the same process, but except we are doing it with lasers, and it's a coherent process. Okay? So we can control it better. Alrighty, so we produce these attosecond X-ray bursts in gas of atoms with a strong laser pulse. We produce a new light, and this is a picture of that set of X-ray bursts that we produce from there. And now we again run into an issue. How do we measure this, right? So again, we use a pulse to measure itself, but we cannot quite do that in this case because the pulse is too weak to split and to combine and measure. So in our case, what we do is we use this technique that we split a red pulse. One of its part generates X-rays. The other part, we leave it as is. Then we combine both these parts in our vacuum system, in our interaction chamber where we are doing the experiments. And we have this detector over here, which is called velocity map imaging detector. So what it does is that it images the electron waves coming from atoms when X-rays hit them. So atoms here emit these waves. And this is a real picture of electron waves from my lab. So there are these beautiful waves that are emitted. So then I watch for what changes are produced in these waves when I change the time between blue pulse and the red pulse, the X-ray pulse and the red pulse. Okay, and based on that timing change, I can establish a beat pattern. So that in time there is a beating that's going on. Okay, it's like two tuning forks or two musical instruments beat. It's a beat like that. So this side is energy of the electrons, and this side is the beat. Okay. And again, now we have to come up with a new name for this technique, and being a hard-working physicist, so we put our mind to it, and we came up with the name, which is rabbit. So for femtosecond lasers, it was frog, now it's rabbit. So it's reconstruction of attosecond beating by interference of two photon transitions. That's the acronym. All right. Okay, so wonderful. So we can produce these pulses, we can measure them, and we can use them. But before we go ahead and use them, let's talk about a little bit about how do they compare with conventional X-rays. We know that Wilhelm Röntgen produced X-rays. He took this in 1895. He took a picture of his wife's hand, the first X-ray. Okay, her ring is over there. You can see that. So now we have refined this X-ray technology. No, but it hasn't changed dramatically. It's about the same X-ray tube. The pictures are definitely much better, right? So, but our approach is to produce coherent X-rays, which give us new capabilities, and we can do that in my lab on a tabletop, and this costs about $500,000 to produce, or we can go to Stanford, and they have a kilometer-long tunnel where they accelerate electrons and they wiggle them, which produces much stronger X-ray radiation. It's not as short as what I have here, attoseconds, this is femtoseconds, but it's much higher energy, kilovolts instead of just hundreds of volts. So they can do it over a mile and produce these X-rays. Of course, it gets expensive, so this is about $1 billion. Okay, so but the point is that we have amazing new type of X-rays now. Coherent ultrafast X-rays, and you can use them to image proteins which are inside us, which are doing all sorts of things. They have lots of functions. We want to study proteins, right? So now you can take an X-ray pulse and shine it on a protein as it's doing something, and the X-rays are going to diffract from the protein, and you can take this image of this diffraction pattern, and you can figure out what the structure of the protein was. What was it doing? Okay, because it's now short pulse, you can follow its evolution. Okay, you can make electron movies, like the basketball movie I showed you. You can make a movie of an electron wave as it is going around. So in this movie, you see the electron wave that's going up and down as it collides with an atom. So this movie can be produced because we have attosecond resolution X-rays now. Okay, And you can control when the electron comes out from a molecule, how it comes out, in which direction. So you can do a lot of physics and chemistry with it. Alrighty, so here is our holy grail. We want to do basic science. We want to study attosecond dynamics, but we also want to relate it to macroscopic function. You excite electrons, they move around, then the structure of the molecule changes. So we want to understand all these processes in a complex system. Okay, so it's a tall order, it's a long task, but that could be really helpful in understanding processes which are going on around us, all around us. So the method, so it's not as simple as just going ahead and take a picture. So when do I know how to take a picture, right? I mean, the molecule is moving so fast, right? It's moving in trillionth of a second. When do I take a picture? So we need a technique, and this technique is called pump probe spectroscopy. So we actually set a time 0 first. We hit a molecule with the light pulse. That starts the thing going. So the clock is ticking and the molecule is moving. Then I come a little bit later and I take one picture. So the clock has moved and the molecule has moved, and I take one picture. Then I come a little bit later and take one more picture of the molecule. Then I come a little bit later and take one more picture. And the clock has started from t equal to 0, and I can stop it at t equal to 5, 10, 15 femtosecond and take these pictures, like the horse that was jumping around, and build a movie of what this molecule is doing. Okay, so that's our technique called pump probe spectroscopy, and I have a demo about it in the front if you want to see it in action in when it's scaled up. How does it really work? Okay, so yeah. So yeah, do come and see the demo after the talk if you're interested. Okay, so there are a lot of applications of this stuff. I talked about photochemistry of vision. It's important in photosynthesis. It's important in photocatalysis. This type of dynamics that we are interested in and we want to study using ultrafast lasers is also helps us understand how the DNA protects itself from the solar radiation, right? So what DNA does is that you excite an electron, and instead of just popping out of the system, it relaxes down back to its original state through this cone, this conical intersection. So these things are of interest to us, like how do these processes work? Okay. These conical intersections that I just showed you in the previous picture, they're actually called molecular funnels, and a lot of processes in life all around us go through these funnels. So this is a very efficient path. So two electronic states, excited state and another state here, can touch each other at this cone, and then this electron can find its way, wiggle through this cone, and it's a very fast pathway for release of energy, much faster than other processes. So it's a very efficient process that happens in our body all the time, okay, in nature. Okay, so we wanted to study this process, but we don't want to go to a complicated system right away. So we start with simpler systems. Like in my lab, we looked at carbon dioxide. So what we do is we come with our attosecond pulse, we create a hole inside a molecule. And then the molecule of carbon dioxide with carbon atom and 2 oxygen atoms, it bends and it stretches. As it stretches, this hole goes through a conical intersection. So it finds its path through there. And we detect it later using a probe pulse, just like what I showed you earlier, pump and probe, okay? Start the clock and stop the clock. So we took this data, and I'll give you one example of this data. So on the left, if you focus on the left here, what you're seeing is that we see an oscillation. This oscillation corresponds to the hole in the molecule, the electron hole, going from one orbital which is sigma orbital here, to a pi orbital. So it flips back and forth and produces this oscillation. And on the right hand side is a movie of this electron going from at the center, and then it goes outside. So it goes from the center, which is a sigma orbital, and it goes to off axis or pi orbital. So we can make movies like that. We work with theorists to understand these basic systems, and then we can carry this knowledge to larger and more complex systems, hopefully. Okay, so I think, am I doing good on time right now? Okay, a little more left. Okay, so maybe I'll show you a few more slides. So we have a bunch of investigations going on in my lab and in the world all around. We look for super excited molecules. How do they relax? If I hit an oxygen with an X-ray photon, I form oxygen atoms, which can then form ozone in return, right? Same ozone that's formed in the atmosphere by the sun, okay? I look at nanomaterials. I look at many kinds of problems, and we use these fancy techniques whose names are velocity BAM imaging, attosecond transient absorption. So again, let's not get into details, but we write papers, which if you are keen or if you already know about this stuff a little bit, you can read them. So, all right. So, and the most important thing here is that it's not just me; it's the students who do the work. You know, young people, and this is the guy who made that electron hole movie, Henry Timmers. So we are pretending to do something here while the photographer is taking the picture. So, but these are the guys who are doing this work, and the instruments we use. It's not just laser. We are using a lot of instruments here. This is our laser. It's a long table. It's about 20 feet table. And the laser can fit on your dining table, but then the rest of instruments here, the X-ray generator, the velocity BAM imaging, the attosecond transient absorption chamber, all this is in vacuum, and it's the other side tables are filled with this stuff. Okay, so it's a lot of stuff going on here, and if you want to unclutter this, this is my basic idea. This is what I'm trying to do, and my students are trying to do. Okay, we are trying to get to these tiny little fast moving things and try to control them. So we are trying to use tools where we can control a molecule, control an electron inside an atom. Okay, so this is what we are trying to do. All right, so I'm almost done here, and I want to come back to our previous slide. I told you all these speakers gave beautiful talks. So the work I described today, femtosecond, attosecond duration motions, okay, the way it relates to all that stuff that we talked about before is that if we understand what's happening in atoms on attosecond durations, if we understand how molecules move around on femtosecond timescales, then we can understand how our biochemical processes are happening, how our eye is perceiving things. Then we can understand how photosynthesis is happening, how things are growing, what kind of reactions are occurring, what kind of reactions, geochemical reactions are occurring. So you can trace it all the way back. So it's kind of a very nice loop here, right? All right, so now as my last slide, and it's about time that we finish the series, and I again want to remind you that please come up front, and I have a demo for you. I'll try to, it's not something that you can kind of show it to everyone. It's not that easy, but maybe after the questions, I also have a movie of this demo. It doesn't come across nicely in a movie. You have to see it with your eye, because the reason is our eye has a continuity, and the cameras, they are not that good actually, to be honest, on the phones and they're not as good as our eye. So you'll see that. And also, thank you very much for listening. And if you have any questions, please feel free to ask. Thank you.
All right, that was really wonderful. Just a couple of things here. As we always do immediately after a talk, we're going to take some questions. Now, you can see there's only me here today. So normally I have two microphones. Today I've only got one. So the general format is, if you have a question, I'll go ahead, I'll pass the microphone to you. And when you're done, go ahead and pass it back. And we definitely have a little bit of time.
Hi, a couple of weeks ago in the Arizona paper, they talked about by the year 2024, they're going to have laser weapons. Can you elaborate on that a little bit?
So the lasers that I briefly alluded to the fact that these lasers have very high powers. They have very high powers that can blow up stuff. And it's possible to weaponize them. There is research in Lawrence Livermore National Lab where they are where they have this, I talked about terawatt laser. they have this petawatt laser where they are trying to create fusion. And the same tool is also being used to understand our weapon stockpile. So they're using the same tools. You could put this laser on an airplane, and the US government did that. And you can try to see if it can shoot down missiles. And you can also try to, so there are efforts that Army and Air Force are already pursuing. It's expensive for this new technology. I cannot predict, but yes, definitely the fact that there are so many applications of lasers, it's almost inevitable that it will have applications in weaponry as well. And how successful it is, how cost effective it is, time will tell. Yes.
You certainly can't know electrons are orbiting around the nucleus. So what exactly are you trying to measure? The vibration
Yes.
of the electron? Since it is a particle,
question.
it also behaves like a wave and vibrates, correct?
That's right. It's a very good question. So, so this picture is, of course, highly misleading, right? These are not these billiard balls floating around. These are waves. And so I'll have to take you a little bit back to show you the picture of what we are really measuring. So let's see. So this movie I showed you, this is what we are measuring. Electron is a wave. As this wave goes out, we are trying to control it. We are trying to study what are which directions does this electron wave go? Okay, what energy does it have? The farther from the center, greater the energy, right? How does it move around? If the wave goes up, does it come back and collide with the atom? So we are basically trying to understand electrons as these waves that are being emitted. But when we detect them at the detector, so there's a duality here, right? So when we detect them, they act like a particle, but in principle, they are these waves that are coming out from our experiments. Yes.
My question is, could we possibly even go shorter and help maybe discover dark matter and things that we cannot find today?
Sure. So answer is why not, right? So there is a lot of room down there. There's a huge amount of room. So there is already discussion about going below an attosecond, which would be zeptosecond, right? So and you can then keep on coming up with the more words here, but the point is every time you go down in time, you have to go up in energy, right? So you have to scale up your systems to produce huge energies. You have to go out beyond X-rays now, right? So if you want to go beyond zeptosecond, we are talking about gamma rays, which nuclei emit. So the problem does approach particle physics. So as these lasers pulses get shorter, intensities get higher, you can study particle physics. And there are efforts where at least there are discussions where people are building laser plasma accelerators to study particle physics. And they want to address some questions, which probably, I don't know if they're related to dark matter, but they are interested in understanding accelerating electrons in a lab on a small scale, and then bombarding them with something and look for interactions. So it's like a mini version of, do you know about CERN accelerator in Geneva, this huge ring? So we are trying to see if we can use lasers to produce high energy particles, which can do some of that kind of work. So yes, so there is a lot of room, there's a lot of research. Investment is the key, and the priority needs to be established. So because, as I said, it's already, the expenses are pretty high. These things cannot be done in a university lab if you go beyond this. You need a dedicated facility, a center which is funded by the government or by some organization. Yeah.
You use your method to excite molecules. How do you know that you have a purified molecule to excite? I mean, what do? Do you concentrate the carbon dioxide that you excite, or?
So we actually we just it's available from the suppliers as ultra high purity carbon dioxide. So all the gases that we're using here, they have different purities: research grade, high purity grade, ultra high purity grade. And the higher the purity, more expensive it is. So we stop at 99.9995% pure. So it's pretty good for our work, but you could in principle purify it more. But we do know when you hit a molecule, what comes out. If it doesn't look like carbon dioxide, then it wasn't carbon dioxide. So it's not like we get confused like half the time. It's maybe once in a while we hit something else, but then we know that it wasn't carbon dioxide. So it doesn't bother us that much.
So you talked about rotational spin.
Mm-hmm.
So you also talk about measure and control. So my question is there any difference when you measure a dextral or sinistral type twist? And are you able to control that?
Mm-hmm.
Are you able to take the rotational direction and change that? And if you can, what implications does that have on a macrosphere?
Okay, so there's two questions. The first one is easy to answer. So yes, we can use laser pulses to excite rotational wave packets. So we can have a set of molecules which were, first of all, they're randomly rotating, because air is hot, that it has some temperature, and the temperature is associated with some energy. So that sets these molecules moving, but they're moving randomly. So we can take a laser pulse and kick them in a way that they line up and they rotate in synchronization after that. So yes, we can control this rotational motion. We can also make them face one way or the other. Let's say we have carbon monoxide. Do you want carbon to be pointed up at a time t equal to 20 femtosecond? Or do you want it pointed down? We can do that. So we do have that degree of control. In terms of its applications, I think what you can do is you can imagine that if you can orient, let's say, all these carbon dioxide molecules briefly for an instant, so that they are all lined up in one way. So you have created some directionality in your system. You have broken the randomness of orientation. So you have created an anisotropic system. Now this anisotropic system could be used to study something else, to maybe, not just fundamental studies. I'm searching for a more practical applications. Maybe you can do diffraction from it in a way that you could not have done from a normal gas. So you can diffract light, you can image light in a way that you could not do otherwise, because all molecules are just randomly moving around.
We have time for one more question, and I see a great candidate back there. And just as a quick thing here, because I want as many people as possible to be able to see this awesome demo, I am going to warn you, there is a strobe light. So if you're very, very sensitive to flashing lights, it might not be something that you want to see, or at least not in real life, maybe a video.
Yes.
I have two questions. The first one is the conical intersection.
Conical intersection, yeah.
Yes, you talked about how the particle can pass through and accelerate. And I'm wondering, on a macro level, could that apply to a wormhole, which would, in the Star Wars era, allow us to travel to another galaxy instantaneously? Let me ask the second one. I'm wondering about current and future applications. You talked about studying proteins, and in research of Alzheimer's disease, I know that if the amyloid protein is present, there's a likelihood that that person will develop Alzheimer's. So what do you do with that information, and how does that relate to your research?
Sure. Okay, so yeah, conical intersection was the first question. So let me see if I can go back. So it is like a wormhole between two different electronic states. So if you imagine electron is living in this state, it has its own universe. This is a different electronic state. Okay, so the electron can tunnel its way through and end up in the other state. This could be excited state, this could be ground state. So it's made possible because electrons are not alone. There are molecules have other motions. They can bend, stretch, and all those motions make it possible for the electrons to hop between this. So it does look like a wormhole, but unfortunately it does not have anything to do with the real wormhole. It's a theoretical construct at this point, and I'm not the expert in that field. There are a lot of conjectures, but they're conjectures at this point. Okay. And your second question was about proteins, and the proteins. The idea is that let's go. So the idea is that if you take a protein and you can get its structure. By structure, I mean you know where every fragment is positioned, okay, where every molecule is by X-ray diffraction. You understand its structure, then you understand its function, because it's the structure of the protein that determines what it's going to do inside the body. So that's why these tools where you get the structure, they help you understand what the function of that protein is. So I'm not familiar with the protein that you mentioned. I'm not a biophysicist either, but I could tell you this, that if you could build a database of these proteins, you would have much more knowledge or power to understand how these proteins interact with the environment in your body, what all they can do. So it's all about, it's like building, so now we know about human genome. So it's like building another database of protein structures, and also how proteins move around in time. If we can understand that, it gives us another degree of understanding of that problem.
And I always ask this question, and if you all remember Aaron asks the same question. Arvinder, what got you into science?
Okay. What got me into science? It's been a while, right? I mean, it's I think curiosity, basically. You know, it was a curiosity about things, how they work. I mean, I didn't come from an environment where you were exposed to a lot of science early on. Grew up in small villages and places in India. But I do remember our physics teacher was very good. He showed us a lot of demonstrations which were almost non-existent, you know, in some sense in schools because of, you know, various reasons. So I got curious, and I kind of used libraries, you know, as much as I could to kind of absorb information. But eventually, you know, when I entered a laser lab, I just knew that I had to do this. You know, it just looked so amazing and futuristic at this point.
Excellent. Well, everybody, let's give Arvinder one more round of applause.
Thank you.
And before we start the demo, I just have two reminders. Many of you saw, we had a sneak preview of next year's Saddlebrook Science Cafe series, but if you didn't, the title that we're working with right now is Putting Data on the Map. And a couple of changes here. We're actually going to be starting our series in October this year, so we'll have 7 talks instead of 6. And for those of you curious about what putting data on the map means, we're looking at data and how we can visualize it. So how do we take numbers? How do we take random strings of code, and how do we make it into something three-dimensional that we can look at, something that we can interact with, and something that we can actually use to change the world? So that's something to be aware of and something to keep on your calendar. Second off, there are evaluations outside, and we really value your feedback. I mean, it's excellent. You have given us so many wonderful suggestions, from what to put up on our stage to changes that we can make to lighting and even minor things like that. So we really, really value that. And the feedback sheets are outside. If you feel like leaving it, no pressure. And again, one more warning, if you're here for the demo, it does involve a strobe. So if it's something that you're very sensitive to, it's something to keep in mind. But with that said, I'm going to let the demo start, and it was wonderful having you here for the Science Cafe. So thank you all so much for coming out with us this year. This has been amazing.
Okay, so I have a tuning fork and a strobe light there, and I'm going to try to get it going. and first try it over there, and then I can try to run a movie of it over here as well. So what's happening here is that this is a tuning fork, and this is exactly the movie we made there. All right, so can you dim the lights a little bit? Okay. Well, actually, can you up the lights for a second? So, can you see this moving? Not really, right? It's moving too fast for you, right? It's the same thing in that movie there. It moves, it's just blur, right? So now, I'm going to first try to show this over here, see if you can see it. Then I'll run the movie, and if someone wants to come here later, they can see that too. So I'm going to run the strobe light on the same thing. And question is, can you see it now? See that? Okay, so I'm going to put a movie up there now. And then we can come back and you guys can try it for yourself to see how fast motions can be resolved by ultra-fast pulses of light. So this is the original movie. Sorry. Someone is going to hit this tuning fork, my student, and you just see something blurry. It's making sound, it's vibrating, but you really don't see how much it is moving, okay? All right, now the second picture is with the strobe light. As I said, the cameras don't do justice, eyes are best, but let's try this. So these are pictures taken like with a strobe light, one after the other. So you can kind of see the motion. But anyway, thank you very much. I'll let you play with it if you want.
You said the basketball was baseball.
Oh, I said baseball? Okay.